Okay, so we've talked about layer 1. Now what happened at layer 1? Let's start. What was the protocol data unit? What was the PDU, the protocol data unit, in the some people fight back at layer 1? Bits, ones and zeros. And at layer 1, we define things like the voltages, the connectors, and those sorts of things. And oddly enough, the wire itself wasn't part of it. Was not. All the other stuff is the voltages that we use, the timing that you use, those sorts of things are layer 1. Why? Because we have different kinds of wire. I mean, if you look at it, we have twisted pair, you have coax, we got fiber, and we even have unbounded media. You know, keep getting those words in. Unbounded media, wireless. The RF signal would be the layer 1 for the wireless signals. And then we talked about layer 2. What happened at layer 2? What were a couple of big things that happened at layer 2, the data link layer? What did we create there? Or actually, let's go back to, what's it for? What did it do for us? You have to go back and do that whole lecture again? What layer are you talking about? 2. Put in frames? It allowed us to get on the media, get on the street, didn't it? Did we define some topology there? Is that where we had to bust the ring and those sorts of things? It's where wireless also is defined. One of the points, hopefully, that you'll take away is, where are these topologies actually defined? Where do we define the bus topology?
What do you mean by that?
Where is it technically defined?
What layer?
What layer? Oh. And what's the standard? You guys wrote a little paper about standard. What is the standard?
The standard is 18 something.
Is what?
18.
How about 802.3?
Yeah.
And what layer does the 802.3 standard get defined at?
3. Third layer? 2. 2. Second layer.
What's how far we got yet, isn't it? 2? Yeah. So the bus topology was defined at layer 2. Where was the ring topology defined?
First.
Really? Where was the ring topology defined?
7th layer.
2.
2. I meant 2.
802.5. Where was the token bus, which we don't really talk about, defined? 2. Where was, I'll go back to Tom's, where was ATM defined? 2. So all of these topologies are defined at, and this, I want you to take this away, at layer 2. There is no difference between LANs, WANs, MANs above layer 2. That's, having said that, there are some of them that overlap a little bit, but most of them are really old topologies that we don't use anymore. But when we talk about LANs and WANs and MANs, initially in Chapter 1 we said, hey, a LAN is what?
Large area network.
No. A LAN.
Local area network.
Local area network, small confined area. Wide area network, large area.
Sorry.
And a MAN is metropolitan area. Where's the metropolitan area network defined? What layer?
2.
We got a consistent answer here, don't we? So the answer to everything is not 2, but today about everything, the answer is?
Layer 2.
Layer 2. So what does layer 2 really do for us?
Everything?
Well, not quite everything, but it does a lot. In the Ethernet, it defined the collision domains, didn't it? And we talked about switches and how many collision domains are on a switch.
Oh, well, there's multiple.
Multiples, every port, right? How many collision domains in a hub? 1. Can we have collisions in a switch? No. Can we have collisions in a hub? Yes. You bet. So layer 2 is a pretty big deal. Layer 2 frames the data, puts it into frames, and lets us get onto the media access control. defines basically whether it's a local area network, wide area network, what kind of local area network there is. Also, wireless is defined at layer 2 also, 802.11, the 802.11 standard. The objectives of this one identify the characteristics, it says, of TCP, IPX, SPX, NetBIOS, and AppleTalk. We'll spend, hopefully, about 32 seconds on IPX and AppleTalk. Reason is, they're not used anymore. TCP/IP is the protocol of the Internet, so that's the one that we use everywhere. NetBIOS is still functional. Microsoft says you don't need it anymore, but not entirely true. The operating system itself doesn't need it, but a lot of applications still do. So we'll talk very briefly about that. NetBIOS basically goes as far as the router to broadcast protocol. When you look at your computer name, the NetBIOS name is the computer name. The fully qualified domain name is the NetBIOS name plus the domain. And here, eCPITech, roanoke.ecpitech.edu plus the computer name would be the fully qualified domain name. The NetBIOS name would be RKE-RM111-001, whatever the computer name itself is. Now, networks correlate layers of the OSI model, correlate 2 layers of the OSI model. Network protocols. What were protocols? That goes way back to week 1. That was before Christmas, right? What are protocols? What?
It's a type of language.
Type of language? Just a set of rules, really, isn't it?
All right.
And language is fine, but it defines how we do things. So protocols, network protocols, are going to be the language, the rules that we use to get stuff. The protocol that we use to get a web page is HTTP. Hypertext Transfer Protocol. The protocol that we get to download files kind of is FTP, File Transfer Protocol. The protocols, the rules that we use to get the information and how this relates to the OSI model. A lot of them run at layer 7, not all of them do. Some of them are at lower layers. The core protocols of the TCP/IP suite and define their functions. They're the ones that are kind of like an alphabet soup, and we'll go through some slides on those. An alphabet soup of things that run in TCP/IP. Identify well-known ports for key TCP/IP services. And if you look at, when you get ready to take this certification test, if you look at the objectives, and there is an objectives document in your one of your folders there in Moodle, it lists the ports, and it lists the ports that they want you to know about. It's not nearly as long as the one that's out there in the hall. The major ones, like the 80s and things like that. Understand addressing schemes for TCP, IPX, NetBEUI, and AppleTalk. The only addressing scheme, again, that we're concerned with is going to be TCP/IP. We're going to take a quick look at it. Next block, we're going to spend 2 weeks on it.
Wow, that's good.
Okay? So we're going to spend 2 weeks on TCP/IP addressing, IPv4 addressing, more specifically. That's where we get into subnetting and looking briefly at routes and things like that. So how do you control the addressing of TCP/IP? So today is just going to be an overview of that. IPX, we're going to spend about no time on. IPX is basically it's a random hexadecimal address with the MAC address of the computer appended to it, if anybody should ever ask. NetWare will assign an address, an hexadecimal address, or you can use other stuff. When we used to do NetWare, I used to use things like, BADDAT. That's a perfectly good hexadecimal address, isn't it? 0 through 9 and A through F. So I can be sure I was on the right network. And then it actually uses the MAC address as part of the addressing scheme. NetBEUI, we'll talk very, very briefly about. Actually, we'll talk about NetBIOS and NetBEUI. NetBEUI is Microsoft's NetBIOS protocol, is really what it amounts to. AppleTalk I'll say about AppleTalk, the only thing I've ever seen about AppleTalk on anything is what does the address look like, and it looks like half of a...
What is a Netbios?
Netbios, it's a network BIOS. It's a broadcast protocol. It is, as we said earlier, when we look at that, there is a protocol that can be turned on or cannot be turned on, broadcast protocol that goes, how far do broadcasts go? Infinitely? No, not really. How far do broadcasts go?
It's radio waves in space.
No, it's radio waves. But how far do broadcast protocols go?
Oh, I don't know.
All the way to the router. Routers start broadcast. So in this room, you would have Netbios, and if I don't know if it's turned on or turned off, and we can look at it when we get done with this part and see. You may or may not be able to see all the computers in this room that are turned on because they're broadcasting their presence. We also have a protocol that allows us to just simply use a server if we only use a one. What it really is a single name lookup. Instead of using RKE-RM111-001, this machine, .roanoke.ecpivab.edu, really long, right? The NetBIOS would be RKE-RM111-001, and it would use a broadcast protocol to try to find that. But it could only find it if it's on this network. If it only goes as far as the router. So a fully qualified domain name we use, and we'll talk about the services we use, a service called DNS to look that name up. And so we could go from, we could contact machines like, like the domain controller.
It can only be on a local area network?
What now?
The
NetBIOS is on a network.
So it could be on a...
I'm trying to be specific. A local area network. There are a whole bunch of local area networks in this building.
Right.
Because each network is a local area network. It's on, but you can only, this room is a network.
Okay, yeah, I see.
This room is a network, and so these machines can only see, if we're using the NetBIOS protocol, these machines. Still looking at me with a furrowed brow. I'm going to start the recording again. With about NetBIOS, different protocols do different things.
Okay.
We agree with that.
Mm-hmm.
NetBIOS is actually a really old, very early protocol that only works inside a single network. Does that make sense?
Yes, it seems pretty useless.
Well, it kind of is and kind of isn't, because when we get through here, we're going to install a service that makes it more usable. We'll install a server called the NetBIOS name server. Kind of got the name in it, right? Mm-hmm. That allows you, because we use the IP address to get there, allows you to look up those names and find the IP address. Once we get the IP address, and that's always a big deal, finding the, because we like names, right? Mm-hmm. You guys, when you go on the internet, how many of you use the IP addresses of the websites you go to? I don't either. We like to use names, and we're going to have fully qualified domain names, which we're going to use a service called DNS, Domain Name Service. And then we're going to have another one for the NetBIOS if we need the service. And the point I try to get there is that the operating systems themselves don't need them. Linux never used it. It's a kind of a Microsoft thing. And up until they claimed Windows 2000, not real sure about that, you had to have it for Windows to function properly. And you had to have that central NetBIOS name service. Issue now becomes a lot of people wrote applications that you use on your network that need to be able to do that lookup, like to find a database or something like that. And it uses NetBIOS name instead of fully qualified domain name. So depending on the applications that you're running on your network, you may or may not need that service running.
Yeah, that seems kind of like engineered obsolescence to me.
Well, it is. Well, it's not engineered obsolescence. It's the protocol that existed before the other ones that were developed. It's like saying that the AM radio was engineered obsolescence. Well, when they put the AM radio in a 1952 Chevy, they didn't have FM radio.
Yeah.
And then when they put an 8-track tape player in your 62 Gremlin, they didn't have CDs. So when we had Netbios, we didn't have all this other stuff. And that's why. That's why they're still there. And then you develop things get developed, applications get developed that need that. And then you move on, so for backward compatibility, to be sure everything still works, you still keep that protocol running. Does that make sense? Because is it engineered obsolescence? Yeah. Not really, because they didn't have anything else at the time when we do those things. Implementation of DNS, we've kind of talked about that. And WINS is the Windows Internet Name Service, is also Netbios name server. We got a couple of, I got a scan that I did real quick, and again, how much traffic is in one. We'll look at some actual traffic that goes on the network. Install protocols on Windows XP clients. We can do that, and that's a matter of, and I'll make you some virtual machines. You can install those. That's just a matter of adding it to it, quite honestly. If you need other protocols in today's world. And they're going back to the IPX, SPX, those sorts of things. In today's world, all you really need in almost all cases, particularly on clients, in almost all cases, is TCP/IP. Microsoft, by default, turns Netbios on. You can turn Netbios off. Why would you want to do that?
Because it's obsolete.
It's not really obsolete. It's still there. It can be dangerous.
Okay.
Because Netbios is that protocol when you go to network places and you double-click and you see all the computers.
Mm-hmm.
That's Netbios. If you turn Netbios off, you know what? You don't see all those computers, and they don't see you. They don't see you, but you don't see them. So it's a way to make it more specific on what we can and can't do, will and won't do with these things. Protocols, purpose, speed, transmission, efficiency, utilization of resources, and this is a big lot of words. A protocol is basically a set of rules. I mean, we have certain protocols that we use in these things. Multi-protocol networks running more than one protocol. Is that a big deal? Probably not so much anymore. In the recent past, and if you go to some place that's still running an old version of NetWare, it is a significant thing, because the old versions of NetWare, which still work, only used IPX, SPX as the protocol, so we could have the different ones running on the same network. And there's no big deal here. Back to the highway, it's kind of like having a Chevy and a Ford on the highway at the same time. It really doesn't matter. They have their own peculiarities. Most popular protocol suite is TCP/IP, and I would venture to say not only the most popular, but probably the only one, and I keep saying probably because people go to strange places that have stuff that they just haven't changed, because when do businesses upgrade? Well, everybody wants the latest and the greatest, right?
They upgrade
when they absolutely have to, when it doesn't work anymore. So if I have a NetWare 312 server running IPX, SPX, and it's doing the job, am I going to spend the money to put in a brand new Windows Server 2008 or 2010 or 2012 or whatever? Not until it starts. As long as it's doing a job, I'm going to keep that. That's why you may, again, unlikely, but you may run into something like that. Netbios, is it going to be there? Yeah. Do you need to use it? Maybe. Depends on the applications that are running on your network. Does Windows need it? No. No, we'll say no. They say they don't. And I think the new ones don't, but not very far back. If you turn it off, it kind of caused some issues. We had an issue here, and they've upgraded it. How do you find out if you needed it? This is my idea to find out if you need it. Turn it off. If it doesn't break anything, you don't need it. If it breaks something, turn it back on. We turned it off, and you know what? Broke something. Broke the view testing program, because the clients had to use the Netbios name to find the database, to take the cert tests. So we turned it back on, fixed it. But do you or don't you?
Kind of like how to, you're talking about, not upgrading. Sears is the world's worst. They still use one T1 line to run voice and data to the whole store.
That's all they need. That's all they need. Why pay more?
They need more.
Well, that's a decision that they have to make, and that's a decision that the network administrator has to make. Is the resource available? But the T1 is a little bit different than what we're talking about here. You're talking about a bandwidth sort of arrangement, and we're moved up in the protocol stack.
In reference to not upgrading.
Yeah, but that's up to the business. When does it need to be upgraded? And that's something that network administrators and hopefully with the users get together and figure out what they really do need. Alphabet soup today. TCP, IP, UDP, ARP. And many others. We'll talk about some of these. We'll look at some of these when we look at some Wireshark scans as we go through this thing. The de facto standard of the Internet, TCP IP. Back to the net buoy. Microsoft was actually working on, it's not a routable protocol. The thing that I love in these books is say that it's really simple to configure. Yeah, because you can't do anything to it. That's about as simple as you can get to configure it. You can't change anything. You turn it on, turn it off. That's it. But Microsoft actually was working on a routable net buoy protocol when the Internet kind of took off and TCP IP became the de facto standard, because that's what runs on the Internet, TCP IP. So that's what we use in our networks because we want the global connectivity in these things. May be able to span more than one LAN are routable. Routable and not routable. Netbios, I know we've beaten it to death, but Netbios is not a routable protocol, which means that it can be used to contact computers within its own network. It's a broadcast protocol. IP is a routable protocol, and that's probably in this part of the class as far as we're going to go with that. We'll look at some routing and how that works in the next one. We'll spend more time at layer 3. But routable and non-routable can run on virtually any combination of operating systems or network media. Routable TCP IP is going to run on everything. Your tablet, the iOS, the Androids, Linux, Windows, NetWare. We did that. The Apple OS is the iOS. All these things run on IP, TCP IP, so that we can have that connectivity. And that's always the big thing. And I'll tell you one thing, when the Internet goes down, you as a network administrator will know about that in about 3 minutes. The server could be down for about 8 days and nobody knows the difference. But if the Internet goes down, you'll know probably in about 2 minutes when you look at these things. Core protocols operate in the transport or network layers. These are the 2 layers, 3 and 4, that are going to get us services. That's what's going to allow us to see the web page, to connect to the server. What did layer 2 do for us? Really? Not now. What did it do for us?
That was the definition of what type of...
What type? What are we using? Are we using Ethernet? Are we using token ring? How do we get onto the media? So it got us onto the media, right? Mm-hmm. And the protocol that we're using at that layer, whether it be Ethernet or wireless, and that basically depends on the hardware that we're using. Once you get onto the network, how are you going to get to your game site? Oh, Facebook. How are you going to get to Facebook?
The TCP IP is
The TCP/IP is going to allow us to get much further. Exactly. Layer 2 is all going to have different definition because we're going to have a wide area network definition instead of a local area network definition. But these things allow us to get to those locations, to get to those services. Reliable data delivery, we talked about that a little bit, and some of you guys have been deployed and write letters. How do you know what sequence? And again, on a mobile unit, I was in the Navy, on a mobile unit it becomes a little bit different, I guess, because all of your mail has to go through the embassy, and some people hold it up longer than others, and on and on and on and on. And if you're at sea, it gets transferred to a ship that may get diverted someplace else. So how do you know that you got everything? You got to have some sort of a numbering sequence. And that's what this provides, reliable data delivery services means. And we'll look at some of the header here in just a minute. I'm going to have a picture of the header information, the TCP header. The TCP protocol, called connection-oriented, you'll sometimes hear it called reliable. UDP is the other end, is called connectionless. And when we talked about that the other day, we went through this. Ken went through we'll go through the synchronization packet, the SYNAC, and the ACK. We actually create a connection before you start the transmission, like a telephone call. Do you start talking on the telephone before somebody answers at the other end?
I always do.
You always do. Do they get the whole conversation then? No. UDP is that way. It just kind of sends the information out. Something else becomes responsible for it. Did it get there? Usually at the application layer. But in this one, operates in the transport layer, reliable delivery, has a numbering system. Did you get all of the letters? Because my letters, I used to get letters, you know, like 1, 5, 3, 6, 4, 2. Doesn't make any sense until you can put the whole conversation back together. That's what TCP does for you. Connection-oriented, you actually create the connection between the two endpoints before the transmission starts. Sequencing and checksums and provides flow control. Flow control means that if you start sending too much information, it sends a slowdown signal. Usually called a choke packet. It says, hey, I got too much. It also allows a negotiation before you start the conversation for something called a window size. How much data can we actually send? How much can you take? And you're going to establish a window size that is at the lowest rate, obviously. Port host addresses where an application makes itself available to an incoming and outgoing data. What does that mean? Port host's address. Whatever port it needs to go to. Layer 4 is where we have the ports, and the ports are related to services that run at layer 7. And to let them in and out of firewalls. And it could be a local firewall or a filter router. There's lots of different ways to do that. Yes, we will do that, but that's the subject of an entirely different area, just that they are there. So we have ports that are related to services. 80 is the one that we all are familiar with because that's the one that goes to the web servers. 443 is the one that goes to the secure web servers. The TCP packet itself, and each of these you say 16, 31, 0, so this is 32 bits is what that represents. Each of these lines is 32 bits, which is, what, 4 bytes?
Sure.
How many bits in a byte? 8? 8? 3?
I'm trying.
Yeah.
I'll get it eventually.
There's two nibbles in a byte.
There's 2 what?
Nibbles?
Nibbles.
No, that's true. That's an actual. That's a term. That is a real term. So we have a source port and a destination port. The destination port is the port at the other end. Obviously, the source port is where it's coming from. See if I can make a mess out of this one too, okay? The source port, if we're going from our machine, okay, from the client machine, the source port is going to be a random port. Which means it's going to be a not well-known port. Well-known ports are those where the services that we know about run. Well-known ports got its name back when there were 8 computers in the world, and yes, that time did exist. And somebody wrote this cool new application called Web Server. And he told all of his buddies, hey, contact this on port 80. And it became well known to all the 8 computers in the world. So those are well-known ports. So when we go to some place, the destination port is probably going to be a well-known port. Something like that. 443. Some service that we know about. 80, and I keep using 80 because that's one that we're pretty familiar with. That's where we'll go for all of our web stuff. Be it things that you want or things that you don't want. The random port is just some arbitrary port above the well-known range, above.
How many ports are there?
Good question. How many ports are there? Remember that number I told you need to know? 65,536.
Okay, so that's how hackers get into your...
That's how hackers get into your...
Because there's so many of them.
There's so many of them, but most of them don't really have anything on them.
Right.
But what they're looking for, honestly, what they're scanning for, if you'll look, is port 21 FTP. That's where, because of file transfer protocol. They're looking for, a lot of cases, someplace to store their stuff, to store the movie that they're sharing, to store the software that they're sharing, that they're giving away, so that they can use those. It's easier for them to upload and download there. What they're really looking for is what's called an anonymous one that doesn't require any authentication. And yes, they are there. So we have a random port, our source port and destination port. When we're going from us, we have a random port, some random port above, the number came to me, 1024 or above, 1023 and below. So less than 1024. And there are some others that run in here. Anything below 1024 is going to be in the well-known area. And if you think about it, that's where they are. 80, 443, 21, DNS is 53, SSH is 22, Telnet's 23, so they're all low-numbered ports. Then they got some registered ports, and I'm not even going to attempt off the top of my head to tell you what they are. They go up to an area. Generally, the random ports, I'll say generally, in a lot of cases, the random ports are going to be something above like 40 or 50,000. But if we got 65,000, that's still a lot of connections. Probably more connections. 15,000, probably more connections than most of our computers are going to handle when we go through there. Then we have a sequence number, and we talked about this SYN packet. And what the SYN packet does is start a numbering system. The sequence number tells us if we got all the data or not. When we send a packet, we'll have a sequence number, and then we got an acknowledgement number. They go together. Because when we have a conversation, we have 2 different directions, right? Mm-hmm. We got the send, and we got the receive. When we do this, and I'll have this in a minute, when we set the conversation up, if we have an us and a server, and we want to have a conversation, we send a packet to it called a SYN packet. And the SYN packet sets the sequence number. What the server will then do is send back, and we call it a SYN-ACK. It's actually an ACK SYN, but SYN-ACK sounds better, I guess. Acknowledges receipt of this number. And then it says, oh, by the way, I'm going to have my own numbering system, because if they had the same numbering system, it'd get really confusing, wouldn't it? Which one did you get? Which one didn't you get? And so it will then send, let's see, send SYN-ACK, and then we will acknowledge receipt of its synchronization number. When we send data, information, or it sends information, we acknowledge receipt of that. And based on the size of the window, we will acknowledge receipt of X amount of data. If we didn't get it all, if we acknowledge receipt of less than what they sent, they resend it. That's how we get the reliability at this layer. That's why TCP becomes a reliable protocol, because it wants to have a receipt for everything that you send. Then we have a header length, how much is in the header itself, some reserved area here. These are called, these are the switches that go with this thing. Urgent, acknowledgement, and when we have a 1 in these things, if we had the SYN-ACK, we would have a 1 in each of those. If we had a synchronization packet, we just have a 1 in it. So these things get set to tell it what's the purpose of this particular TCP packet. And that's what these things are about. Urgent is urgent. Push is one that you may see. Push says, don't wait for the storage area to build up and get full before you send it. Send it immediately. You'll see that if you watch something like, maybe if you're watching stock price streaming or something like that, because you don't want to wait until the buffer gets full, because buffer might not fill up quick enough, and you kind of like to know those prices as they come. So push says get things out right now. The reset here is a hang-up. If you see a fin reset, the reset says there's something wrong. I'm just going to quit right now. A fin says that we're done with this conversation. I've got all the data. I've looked at my web page. I'm ready to close it now. So we'll do a fin, and the other guy will acknowledge, and they'll send a fin and an acknowledgement. So it becomes basically a four-way handshake. Sliding window size, how big is the window going to be? How much data can we send? If we've got a really old machine, it's probably not going to be able to take as much data as a newer machine, as something like you guys would have. What we have to do is settle up on how much data can be transferred in one chunk. How much can it do? There's no saying you got to eat the elephant one bite at a time. What this says is how big is the bite going to be. And the sliding window size. The checksum is just simply the checksum. That's where we get some of the reliability. Checksum, we send the information and you use the same process at the other end to see if the numbers are the same. Urgent pointer, if there is urgency. Options, if there are any options. Probably not going to have anything here, quite honestly. And padding. Padding is important because each of these has to end on a 4-byte, a 32-bit boundary. So if we don't have enough information here, padding goes in to be sure it comes over here to be 32 bits. And that's all that's about. And then underneath there we have our data. Data is the information that we're trying to encapsulate. So we have data and all these things. This is the TCP header. A lot of stuff in it. There really is a lot of stuff in it. Say what? This is what makes TCP IP, they go together, reliable. This is what ensures you get all of the information at this layer. And the big thing, the sequence number and the acknowledgments, and that's what the whole thing's about. And these just, the function of it Source port, destination port, that's not a big deal, right? That's a port number. Sequence number. We're going to start a numbering system. And when you look at Wireshark, it may be a relative or an absolute. If it's a relative, and I'll go through how to turn it on, relative is not really all that helpful.
I've seen something like this before.
Huh?
I've seen something like this before.
Yeah.
On the PlayStation.
Yep. Acknowledgement says that we got this. We got the information that you said you sent. This, the header length is just how much is in the header, so that you know how big it is. Reserved is still reserved, is still reserved, is not used. And then these things over here, what's the function of this packet, is what this is talking about. Window size, how big is the window going to be? The checksum is just something to verify that it's not been corrupted en route. Urgent pointer, maybe, maybe not. Options, maybe, maybe not. Padding to be sure that it goes all the way to the end. And then the data is what we're encapsulating in it. In it. This has got some information. The source port, Holly, this one's coming back from a web server. The source port is 80. So what does that tell us?
It's an internet.
It's an internet. Not only is an internet coming back. That didn't work out real well, did it?
Not at all.
Kind of blotted it out.
Kind of blotted it out, yeah.
Redacted.
Yeah, redacted. Well, let's try this way. So we're going, source port is port 80. That means we're probably getting an answer from a web server, right? The destination port's 1958. That's the random port that we would have initiated the request from, because you don't generally just go on and somebody sends you a web page, do you, unless it's a hacker. I mean, everybody ever get on and somebody just magically sent you a web page?
No.
Me too. So this is going to be where we came from. The sequence number and the acknowledgement number. The sequence number is the numbering system. Remember, we got two numbering systems. One from us and one from them. The sequence number is what we sent. The acknowledgement number says, hey, I acknowledge receipt of this X data. Send the next one. I'm going to look at some where we actually do send some data, I hope. The header length, 24 bytes. So it tells us how much information is in that header. And then the flags that are set. This is got a send and an ACK. So that's, what's the send and an ACK?
Send and then the acknowledgement.
Acknowledgement. Where did you see that? And we're going to beat this one into you also, okay? It's called a three-way handshake.
Oh, yeah, I remember.
We had the send ACK, and the ACK. And the only time you're going to see these together is in that handshake. The send ACK, the window size, 5840. How much data can we actually send? So we've negotiated the window size in here. We have a checksum. It says the checksum's correct. Options, 4 bytes. And so the maximum segment size, 1460 bytes. So it's defining a lot of things that are available, can be used in this thing. Got to get back to the. So the send ACK, and what this is saying, and I want to do this. I want to show one demo, and then we'll take a break here in just a second. Honest, we will have breaks today. Short ones, no. So this one says, I want to start a conversation, a three-way handshake here, right? And the thing that starts a conversation is the send packet with the sequence number, 979370135558. Send. So this guy comes back with the send ACK. This is the only time, didn't work. don't really want to do that. Redacted it again. But what I want to try to do here is this one is 8937013, whatever they start with. This one is 9. This is called the phantom byte because when you send a sequence number in the acknowledgement acknowledges how much data you actually received. In the three-way handshake, there is no data, so it gets incremented by 1.
It has to.
It has to. Yeah, it has to be incremented by 1. Because if we use the same number, it'd really get confusing again.
But isn't it I don't remember, in the acknowledgement, you would think it would be the exact same to say, yeah, I got your message, this is what it was.
What we would do is if we sent something to here that was, say, 100 bytes of data, how do we know it got there? With the acknowledgement. So what if I say acknowledge 9370155.9? Just increment it by 1. How much data got there?
Well, nothing got there yet.
That's why the increment is by the amount of data that was actually received.
Okay.
But when we do the initial setup, there is no data transferred. We're just doing in a phone call the hello, this is, and we're not really got anything in there. Has to be something. We have to increment it. We need to increment it in order to say, yep, I acknowledge receipt of this, but there wasn't any data in it. So they call it the phantom byte because there's really no data here, but we increment it anyway. And then this guy establishes his own sequence number. 304-395-8669. And we acknowledge again with the phantom byte from the 69 to the 70. And the sequence number, it says acknowledge with sequence number. The sequence number here is the same as the acknowledgement number in the previous packet. The change is on the acknowledgement. I acknowledge receipt of this. Because if I send 100 bytes and I only acknowledge 50 bytes, I got to send it again. That's TCP. That's what makes TCP reliable, connection-oriented. Connection-oriented, I think, is a better term for that. But that's what makes it the, quote, reliable, unquote, protocol, because it acknowledges receipt of all of the data that goes through it. UDP, I like this one better. How about you?
A little more simplistic.
That's why it's less reliable, though, isn't it?
Less reliable.
Because it's simpler.
We'll use the unreliable term, connectionless protocol. Because what don't you see in here? I don't see any sequence numbers, do you? I don't see any switches, do you? I don't see any urgents or sends or syntax or any of that other stuff. Yeah, it's called unreliable, lots of different terms. Connectionless. The reason source port, destination port, length, and remember this is layer 4 we're talking about here. We'll have an IP address, but that'll be at layer 3. So the source port and the destination port, UDP, separate protocol. It's not really a send it out there and hope. Something at the application layer is going to be responsible for the reliability here.
But if it's not received, there's no way to see.
Yeah, the application, whatever the application's using, will say that. We'll tell you that. Trivial file, TFTP, is the one that we use predominantly, and it's used to like transfer configuration files from routers to a TFTP server. If you don't get it, the server itself says, I didn't get it. But the layer 4 doesn't tell you that. What I want to do here is look at this demo. It's called the Tcp Sliding Window. How much information can we see and how much are our losses in this thing? And we can set these things down here, loss percent, the window size is, if you notice, the window size, the sliding window size, how much data can we send? That's negotiated by the machines at startup, and that's going to be one of the things that will be defined in all of the negotiation process. So in order to have a little bit more information, and then how good's our connection, what's our loss percentage and our speed. I'm going to make this go relatively fast so it doesn't sit here and go slow. But let's go with no loss. As we start this thing, the data gets sent, and then it gets acknowledged, and it gets sent and acknowledged. Okay? So that's the TCP portion of it. Every part of it, part of the window, because the window is going to define how many of these, how much information can go in this. And we've got a thing that eventually called Selective Acknowledgement that says I didn't get this particular one sent in. So if we had some losses, let's say that we had, and let's make it a bunch, let's make some 20% loss. Maybe slow it down a little bit so we can see the losses. We send these things. Oh, they all got acknowledged, right? Uh-oh. Didn't all get there. So now we got to resend it, and we still didn't get it all there. Now we resend it again. Boy, this one's being a pain, isn't it? And we still didn't get, oh, we're going to get there now. Now we got all the information, we can move on. So it has to be acknowledged before you can move on in the conversation. Does that visually make some sense in kind of in the acknowledgement world? And that's what that ACK bit's all about, and how much data you're sending. How much of it did you actually get? Questions to this point? Yes, I know this is hopefully quite a bit of information, but there's a lot there. TCP, layer 4 layer 2 and layer 4 are pretty complex layers, both of them. So let's take a break. Do what I wanted to do. Okay, IP. Again, I'm not going to spend a lot of time on IP, except this is IP, because we're going to spend a lot of time on IP in the next half of the class, the next block. Information about how and where data should be delivered. It's the address. Each of your computers has an address. And in this room, each of the computers' address starts with 10.60.211. That's the network address. And then you have a host address. And we'll go through the whole how do you get from that to the MAC address, some of it as we go through here. Data source and destination address. The source address is the IP address. The destination address, obviously, where you're going. Network layer protocol enables TCP IP to enter network. And remember when we looked at the 7-layer and versus the 4-layer, the 4-layer they call the network, in the 7 layers, the network layer, the inner network, because it allows networks to communicate with each other.
Okay, so TCP and IP are protocols, right?
Work together, exactly.
If there's a network layer protocol, are they the same?
IP is the network layer protocol.
Okay, so the network layer okay.
IP is and IPX is and different layers. Well, what does the network layer allow us to do?
Okay.
I mean, really, what does it allow us to do? Any guesses?
Allows us to
find other networks.
Okay. Okay.
So if you wanted to go to room 108, you notice I can't resist this thing. In here, our network is 10.60.211, and we'll put .x because X is going to be, each computer is going to have a different number. If we wanted to go to, let's even say the DNS server, we'll throw some terms in here. The DNS server is 10.60.1.4. The X in that is 4, I believe. If you wanted to go to www.facebook.com, which you can't do in here, right? Do you know the IP address? No. Where are we going to find the IP address? DNS server, which is a service that's running on that computer. But how are we going to get there? because this number, and there's more to it, and because we can define it, and this number are different. They're on different networks. The network layer is what allows us to put a router in between here, and be able to send it to a different network. Once it gets to that network, it uses a protocol called ARP, Address Resolution Protocol, to find the MAC address. The only thing network layer does is finds the network, really. And then once you get there with that source address, you use the ARP protocol to find the individual computer, because that's the MAC address, supposed to be unique, right? If you want to have some fun, set a bunch of MAC addresses the same ones and try to troubleshoot it. It's like impossible until you do the, let's look at all of the addresses and say, all these IP addresses have the same MAC address, doesn't know where to go. Sometimes it'll go here, sometimes it'll go there. Because we do, that's how we actually get down to the final layer. But the Internet Protocol, layer 3, the IP protocol is the one that does that. Yes, it is a protocol. TCP is a protocol, runs at layer 4. IP at layer 2. So what was the PDU for the Internet Protocol? Some people fight back, right? Transport segments, data packet, or IP packets, and then data frames down here. So those are those. But that's kind of an overview of, the network layer protocol. IP is the one. Are there other ones? Sure, there's IPX, AppleTalk, things that we don't use anymore. NetBUI is actually a layer, Netbios is a layer 2 protocol.
Something we don't really use.
Something we don't really use. I said I may have lied to you on that one. I have to check that.
The reason why I'm asking this question is because one of the forums is about protocols itself.
You just pick one.
You just pick one and discuss it.
Here's something that you may see on tests, and it is good to know. Unreliable connectionless protocol. What was the connection-oriented protocol?
TCP.
When we combine it with TCP, now we have a reliable delivery. And that's why you usually see them, always see them together, right? TCP, IP. If we had UDP and IP, what would we have? Connectionless, sometimes called unreliable, at that layer.
So it's always paired with layer 2 and 4?
2 and 3, or 3 and 4, excuse me, 3 and 4. What we're talking about is IP is layer 3 and TCP is layer 4, right? And in the delivery of data world, that's as far as we go. Because a router works at layer 3 and 4. It's a layer 3 device. We can filter on ports in it. So, when we're delivering data, this is as far as we're going to go, right? If I can get back into this thing now. IP datagram, packet in context, TCP IP, the envelope for the data. And all this stuff is encapsulation. What encapsulation means is that we start out at the top with a little bit of data, right? Going down this thing. So we start out with a little bit of data, and then we add a header, and everything encapsulates it, puts it in an envelope. It encapsulates the data as we go down. When we go back up, they call it decapsulate it. Take it back out of the encapsulation. So the envelope itself is going to be the encapsulation of this stuff. The header, again, this one we'll do too, but the header, we got a version. We have a grand total of 2 versions, and the only thing you're going to see right now is 4 in here. So IP version 4 is the one that we're using. IP version 6 is available. It runs natively on Windows and all that other good stuff. Internet header link, differentiated services, total link. So we're just defining the version and how big stuff is up here. Identification in here, flags. We have any flags? Fragment offset's kind of a different thing because if it's too big, the packet's too big, it IP, and I'm going to say theoretically because most of them now do not fragment, will break it up into smaller chunks. The problem with that, and the reason that most, like all of your conversations now are marked do not fragment, because that's a great way to hack a system. Because all it has is a fragment offset. You notice you don't see a sequence number in here. Which fragment is it? Just how far into the packet it is. What that means is, if I can do that, says that the first fragment may go to, let's make really big numbers, to 2. So it says that the second fragment starts at 2. The third fragment starts at 3. What if I'm done? What if I'm a hacker? Say, hey, the next fragment, my fragment starts at 4. So I can insert my traffic into a fragmented conversation. It's also a way to get past filters, intrusion detection systems. If you break it up, then you can't read the whole thing, because the device that reassembles everything is the destination device, the computer. So if we have something to check for bad guys on the network called an intrusion detection system or an intrusion prevention system, all it sees is the fragments. It won't ever see any intrusive traffic. That gets put together on the machines, because there's just too much traffic to put it all back together. And this thing has 2 flags. So there's flags here. It's got more fragments or last fragment. That's the only flag that are available in it. The offset is here, fragment offset, how far into the packet does this fragment belong, so that it fits everything together. Time to live, we talked about that at layer 2. If we got stuff going around, there was no way to shut it down, right? Here we have a time to live so that packets don't live an infinite life on the internet. Can you imagine how many we'd have out there now if we didn't have something to say? Well, if you don't really know where you're going, then eventually you're just going to go away. Yeah. That's what that is. And each time this goes across a router, it gets decremented by 1. And when it gets to 0, it goes away. So that's what does that. Protocol, which protocol are we using? Source IP address, destination IP address. These are binary numbers, and we'll get into all that again as we do the 2 weeks worth at the start of the next block, how to do the conversion, how to set them up, how the computer reads these things. Source address is the IP address, the dotted quad, 10.60, in our case 211. I think mine's 177, and my destination address 10.60.1.4 or something else. So source and destination IP address. And notice here we go from 0 to 31, which gives us, again, 32 bits, 4 bytes. It's really nice that all these things are 32 bits wide. And we have the padding option here so that it ends on the boundary. Because they don't know what to do. The computers don't know what to do. Computers are really stupid, by the way, aren't they not? Because unless you tell them what to do, they don't have a clue. So these things, now we have options and data down here. Data, everything's going to have data. Data is everything that it encapsulates. It's not just the data from the top layer. It's the whole package that we encapsulate with this thing. Now we'll look at some of that header. This is theirs, and these are in the book. The header length, again, we have the header length differentiated services field, and this thing's has changed. The differentiated services, I think, is the name it's using now. It's changed names a couple of times. The total length identification, and notice we have the 2 fragments. Two fragments. Yeah, the 2 flags. Don't fragment set, more fragments not set. Should be one's last fragment too, so that it knows when it's got everything. Reports on successes and failure at ICMP. So now we're going into specific protocols. ICMP. It's the packet ICMP Internet Messaging Protocol. I'm sorry, I'm thinking ping here. Network layer protocol that reports on the success or failure of data delivery. You ever get a message back that says network unreachable? Host unreachable? That's what this does.
Error or something based on that?
It's error messages, yeah.
Error 501.
Yeah, ICMP messaging protocol. Yeah, well, yeah, there are a whole bunch of flags in this one. The error messages. What do you want to allow? What you don't want to allow? Those things. So this is what allows the TCP IP protocol to say something's wrong and what's wrong. Network not, host not available, host not reachable, network unreachable, all sorts of different messages. There are. It's got a lot of different flags in it. IGMP, network layer protocol that manages multicasting. Multicasting is when a process is set up to send it to multiple machines at the same time. You're, in most cases, not going to be the one to configure that. The one exception that I can think of is if you're doing network installs on Windows 2008 on up, you can do a multicast for installing computers. So it starts out with the PXE install, PXE way down, a pre-executable environment, pre-execution environment, and sends the software to the machine. You basically log onto the network through the NIC. And it just sends it out so that if somebody joins the conversation late, they get the information, it starts over, they get what is available from the time they get there, and then it starts over and they get the rest of it. So multicast multiple machines at the same time. We've got multicast, broadcast, and unicast. Unicast is one computer to the other. If you go from here to a web server, it's a unicast traffic.
Like one trip.
One destination address. A broadcast, if we did a broadcast in here, and we'll get around to the addresses again when we do the IP stuff, you would send it to every computer in the room. A multicast would be to selected computers in the room, basically the ones that join your broadcast or your multicast. Routers use IGMP to determine which nodes belong to the multicast group and then knows which ones to send it to then. ARP, Address Resolution Protocol, we've seen that one before. Has anybody ever looked at the ARP protocol? No. Go to, let me see if I can do this here and just do the one here. ARP-A, space -A, if I look at that, it tells me where I'm trying to find stuff, the IP address, it translates the IP address to a MAC address, a physical address. 1062.11.1 is the router. That's the way we get out of the room. So in order to go to the web server, the DNS server, the any of the servers, the domain controller, any of those, I have to go to this physical address, which is the router. 1062.11.73, that's one of you. This is your MAC address. 255, this one is going to be the broadcast address. This is the IP of broadcast address. 1062.11, and notice that its broadcast, its MAC broadcast, is all Fs. All Fs is the broadcast address. 224s are going to be multicast addresses. 255 down here, again, is a broadcast. This one's got a number. It says interface 192.168.192. It's got some virtual addresses on it also. We go through a similar process, but ARP translates IP addresses to MAC addresses because we need the MAC address to get to where we really want to go. Can more than one machine have the same IP address? Yeah. Not at the same, yes, but not at the same time. If it as it at the same time, the IP will look around and say, oh, you got mine, and there is a way, they're supposed to check to be sure that it's not a duplicate before it hands out addresses. So, the ARP protocol, address resolution protocol, translates IP addresses to MAC addresses, to hardware addresses. Logical to hardware. Reverse ARP goes the other way around. Reverse ARP is if you really for diskless workstations, if you don't really have anything. You know your device doesn't know its IP address, can use ARP, reverse ARP to find its IP address. Says, hey, I don't know my IP address. Who knows what my IP address is for these things? It's 32-bit number, 4 octets, and again, this is one that I think that I just want to go through basically. The overview here, this shows 3. There are 4 classes of IP addresses. The routable ones are A, Bs, and Cs, and the difference between them are how many networks are available versus how many hosts are available. We have 4 octets, which means that we have 8 bits in each of these things. And you notice the way this goes, we have fewer networks but more hosts per network. We have extended the number of networks and reduced the number of hosts. When I say hosts, computers, printers, router addresses, individual addresses are going to be hosts. What we're going to use mostly are Class Cs. When we go here, and we're going to have available here 255 total addresses on each Class C network. 253 of them are usable. So the classes, there's also, this is A, B, C, there's also a D and an E, which we can't use. E is the experimental, and there are lots of stories about what it is. It's for the military, it's for this, it's for that, it's for whatever. The bottom line is we can't use those two. The Ds are multicast, which we can't use to address. These can't use to address devices. Telephones, computers, printers, routers. What else would have an address? Switch. What else could you think of that might have an IP address? Your refrigerator? No. It might. It will eventually. Some of them actually do. What about a vending machine?
Yeah.
Sure.
Sure. If it's going to take your debit card, it's got to, doesn't it? How else is it going to go charge you for it? ATM. Yeah. So.
I wonder if there's people that hack.
Yeah, more. Yeah, there are. Yeah, more and more devices are getting IP addresses.
They did with code and took all the money out. And that's on YouTube. Oh, you can learn anything on YouTube.
Yep. Especially how to get to jail real quick.
Yeah. I wouldn't say do it. I'm just saying it's on there.
I arrested this guy one time. He had broken into all these coin machines and he had stolen $60,000.
$60,000. That's a lot of coins.
How much did you spend it all up on dough? I said, how much you spend on dough? He said, I could have probably had a couple brand new Cadillacs. Yeah, dude, it's like a cycle. You go break into a vending machine, smoke crack, sleep, break into another vending machine.
This line here is wrong. Many internet addresses go unused. I guess maybe it's kind of is and kind of. Many don't go unassigned. All of the IPv4 addresses have been assigned. So are we running out of them? Yep. There are other techniques, and again, in the other classes, we'll talk about how we do that to conserve IP addresses. IPv6 and IPv6. I've been hearing for about 10 years now. We're going to have to go to IPv6 next week, or not literally, but it seems like it. We're going to do it. Eventually, we're going to do it, but. It has 2 to the 128th addresses. You can figure that number out because I never can remember it. What it basically means is that there are more addresses, and this is the things I've heard, more addresses in IPv6 than there are grains of sand in the world. So we theoretically won't run out. Of course, when they did IPv4, we theoretically wouldn't run out then either, but we did. So IPv6 is the new one. It's coming. It's not coming next week. It's inevitable for now until forever. And if you look in here, if you go up front and look at that little display, you'll see some IPv6. The routers really take care of a lot of IPv6 traffic assignments.
What is the benefits of having it? Are you using?
It is more efficient. It has security.
Okay.
It actually checks the path before you send the traffic to be sure that it's clear that you can actually get from point A to point B. And you have a lot of addresses. Because we're going to get that. When we talk about, does your refrigerator have an IP address? Not yet, but it will at some point in time, honestly. How many devices do you have that have IP addresses, really? But your smartphone does, huh?
Yeah, laptop, phone.
Laptop, phone?
Maybe even television.
Maybe televisions, we're going to get there. And then we just keep, Xbox with the number of IP addresses that we use is increasing really, really quickly. And people are, at the tablets, tablets are just exploding, and smartphones are exploding. So you need the addresses because we really have issued all of the IPv4 addresses. Doesn't mean that they're all actually used, because there are some people that were at the early part of the internet have a lot of big ranges. Since A's, if you have like 10 million addresses in each Class A network, if you had a Class A network, you got a lot of addresses. Even a Class B, 65,000 addresses in each of those, because that's 2 to the 16th. IP config, to look at your view of, and you may or may not, have you guys looked at the IP config? In Linux, it's ifconfig to do the same thing, to look at that information. Decimal number between 0 and 255, binary octets, we kind of talked about that, and again, I'm going to do the overview, but we're going to really get into this in the next one. Subnetting, the subnet mask, there are 2 parts to an IP address. It's the IP address itself and the subnet mask. All the subnet mask tells us is how much of the address is network and how much of it's host. So we had those A's, they were all fixed up. The A's, the B's, and the C's are all 1 octet, 2 octets, or 3 octets long for the network address. For the rest of the world, if we subnet, and again we'll do that, I just want to introduce the term here briefly. If we have a network address, and I'm going to write something in binary, don't panic. Because to make any sense, this has to be in binary. If we have 1, 0, and I don't even know what they are, 1, 2, 3, 4, 5, 6, 7, 8, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8. We'll go down here. Oh, we won't either. Yeah, we will. 1, 2, 3, 4, 5, 6, 7, 8. If we translate that from binary to decimal, we'd have some number, 10, 60, 211, something. That's not what that's going to be, obviously. The mask is going to be something like 255, 255, 255, 255.0. The subnet mask. That is for a Class C network, which means that we would write 1s, and 250, just trust me. 255 is all 1s. It's 8 1s. That's an easy one. So you already got your first binary conversion, right? Eight of each of these, and down here we would have all zeros. What this says is every place that there's a 1 in the subnet mask is part of the network address. So it tells us how many bits are in the network address. The advantage there is we can change that. We said in this one there are 255 total addresses, right? 2 to the 8th. You believe me? 2, 4, 8, 16, 32, 64, 128. Add them all up. 255. What if we needed more addresses? Sure. What if we put a 0 here? The host addresses are all zeros in the subnet mask. Network addresses, we said that the subnet mask, where there's a 1, defines whether it's part of the network. So all we're doing is manipulating this thing. The subnet mask tells us how big our network is. What if we needed more networks and fewer hosts? We just go the other way. Just add a 1 down here. Fewer bits per host, going to be fewer of them. More bits per network. But that's what subnetting device, a 32-bit number. Subnetting is subdividing. Subnetting is actually like, if you go out here to the, vending machine and you only got a $20 bill, do you put it in it?
No.
I don't either. Well, you need a $1 bill? So you need to take a $20 bill and break it up into dollar bills, right?
Yeah.
That's subnetting. That's all you're doing, except with network addresses, you're just breaking it up. That's right. That's exactly what it is. That really is what it is. Or four quarters for $1.
Just do it.
Each of them have a unique IP address. We know that. We've talked that I think hopefully. Static addresses are manually assigned. Static addresses mean that we go in and actually type them in. Not a good way to go because does anybody not make typing mistakes? I do. Everybody does. And that's why you want to assign them with a service, and the service is going to be DHCP, Dynamic Host Configuration Protocol. All these terms that you've heard before, right? These things do. Automatically assign them to DHCP server. Boot P is the original one. Central list of IP addresses associated with MAC addresses. Dynamic addressing, application layer protocol, Boot P is. Client broadcast, the MAC address, and the Boot P. So Boot P, what you need to know, is the original DHCP. DHCP is what we use today, Dynamic Host Configuration Protocol. Automatically assigns an IP address. Because you guys don't have to put IP addresses on these machines, do you?
No.
They just happen. How do they just happen? DHCP. The network administrator has to configure. If you don't have DHCP and it looks for it, you get this really weird 169.254.something address. What that means is that the computer tried to find a DHCP server and couldn't. It's called an APIPA address, and it's a Microsoft sort of thing. It's application layer protocol, the time and planning, on and on and on. But basically what this does is automatically assigns IP addresses to the machines themselves. The DHCP is and what this is showing is a 4-step process. Another acronym. DORA. When a computer and it says, this is client A, going to the server, what IP address can I use? This is called discover. Discover packet. And it comes back and says, hey, you can use this address. Where's too high? Client A, use this. It's called an offer. Both of these are broadcast. They have to be broadcast because nobody's got an IP address yet. Or this guy doesn't have an IP address yet. So it has to, so what it broadcast says, hey, any DHCP server out there, give me an IP address. And the first DHCP server that gets the request sends the address back. Then we have, this one goes back to it and says, where we go, this is client A, I'll take that address. It's called a request. And that says, this one says, okay, and that's the acknowledgement. So it's a 4-step process to get the address. The first 2 are broadcast. The last 2 are unicast because we now have the IP addressing in this thing. And I say that some are all broadcast, some are not. Some operating systems, depending on which one you have, honest. So I've seen it around here operate both ways. APIPA talked about that. It's a Microsoft thing. You get a 169.254, mean you try to get a DHCP address and there's nothing answered. So the computer becomes its own DHCP server and assigns it. We talked about ports early on, 0 to 65,535, which gives us 65,536. Because remember, in the tech world, 0 is a real number. So we have these things, sockets and ports. When we put together, socket means an IP address and a port number is a socket. Port number plus the machine's IP address. Go back here real quick, because I went too quickly there, didn't I? The well-known ports, 0 to 1023 and less than 1024. 1024 and above are other. There are other ranges, but the well-known ports, the web servers and those kinds of things are in the well-known area. Registered ports, 1024 to 49151. The well-knowns and those are there. Dynamic and private ports, 49152 through 65,000. Sometimes you'll hear this called dynamic, you'll hear them called random, you'll hear them called ephemeral ports. It means they're temporary, they're just used, and those are the ports that you're generally going to get for your outgoing from your machine, your random port. IPv6 is slated to replace IPv4 at some time, maybe before I die. Millions of, I said it's been going to be there. It is a simpler header than the IPv4. Has a lot more addresses. It does have security, and that's one of the advantages. When we get into IPv4, we have to add security to it. DNS we've talked about, right? What does DNS do? If you can guess it, I'll click through. What does DNS do? Everybody's got a name. What it does is takes the name and gives you a number, an IP address. Because do computers understand English or Chinese or Japanese? They understand numbers. So we have to get numbers, and that's what this thing does. It takes www.yahoo.com and gives us a number associated with that address. So it can be routed on the internet so that we can actually get there. And these are going to be what are called fully qualified domain names. That's different from the Netbios names. The Netbios name is single name. Fully qualified domain name is the Netbios name plus the domain name that would go in there. www is actually a computer. It represents a single, actually probably a lot of IP addresses, but it represents an IP address. The hosts file is a file that is still available. This goes back to, remember we talked about, or I talked about earlier, and everybody just said, okay, when there were 8 computers in the world, how did they find each other? You could probably memorize their addresses, but they didn't want to. What they created was a text file called hosts with no extension that listed the IP address and the name. This is the first place the computer checks. I had a security class that had one female student and a whole bunch of guys, and they were harassing her. And one of the guys that was harassing her in particular left his computer on and went on break. So she went in and found the IP address of Barbie.com and put that IP address in for like ESPN and all those other places they would go to. So when he went to ESPN, it translated it to the IP address and he went to Barbie.com. So the hosts file is available. If you wanted to, for instance, not type, was it roanoke.ecpi.net as Moodle, right? You could at home go open your hosts file and put, and I don't know what the IP address is, you have to ping it first to find the IP address. Put the IP address and then Moodle over here, and then all you have to do is type Moodle. It'll resolve it for you. So this is something that will resolve. It actually gets loaded into the machine first. DNS domain is a hierarchical arrangement. 13 root servers. It sounds like there are only 13 servers. That's not really true. There are hundreds of them. There are 13 different areas that they go to. The DNS we kind of talked about, I guess, a little bit. The root server, the root is at the top of the internet. And the root's represented by a dot, quite honestly. So we have a dot. And if we're going to go to, I'll do my own. Let's say we want to go to roanoke.ecpi.net. You're at home. Your machine doesn't have anything cached. It has no addresses stored. First, it'll go to the root. And the root will refer you to the net server. Give you the address of the net. You then go back to your DNS server, actually. Then goes back to the net. And the net refers you to ECPI. And then the ECPI server will have a listing for Roanoke, whatever the IP address is. So it's a hierarchical arrangement that replaced the host file. Because can you imagine trying to put all those addresses in your host file? Me too. So you have to have some sort of a lookup, some sort of a directory service in order to be able to find those addresses. And that's what that one does for us. So it resolves it hierarchical basis. There are two types of lookups. A recursive lookup is going to just tell it that, just give me the answer. That's what computers ask for. DNS servers do an iterative lookup, which is the go to here, find that address, go back, find that address, go back, find that address, till it gets the final answer. It gives you the final answer, the recursive answer. Iterative is one at a time. DNS servers do iterative lookups, and they give us the recursive answer. Dynamic DNS just simply means that we register our own addresses in the DNS server, and that's what the Active Directory does for you, because they change periodically. So the system allows them to automatically change. Zero configuration protocols designed to allow us to not have to go through a lot of the things that we used to. Zero configuration discovers available servers, resolves addresses, does a number of things automatically. And it's a service that generally runs on the computers themselves. So now that everybody's soundly asleep, let's take a break. Talk about no, it's not that many. Talk about the TCP application layer protocols. What do the application layer protocols do for us before we go into them? Huh? Format software. Help us out, Jerry. Or Tom, Jerry. Well, I had his brother years ago, who's Jerry.
Jerry?
Yeah.
Tom and Jerry.
So what's there? Say the magic word. The services, right? Abracadabra. How about services?
Yes, sir.
What kind of things ran there? Web servers?
Mm-hmm.
FTP servers? Mail servers? Application layer protocols. The application layer protocols are actually associated with the port numbers at layer 4, because port 80 takes us to the application HTTP, which runs at the application layer.
You can spoof emails using FTP, right?
No, you have to use an email server. Okay. It's a service that runs on a server.
Okay.
FTP is just a file transfer protocol.
Okay.
Now, we'll do some other things. You can't actually telnet to some of these other stuff, but that's things that we'll do much later. Telnet, terminal, speaking of which, Telnet. Telnet allows you to get a command line connection to stuff. Generally, where it's going to be popular is Telnet to a switch or a router to do remote configuration with it, because it's a really basic, non-secure, TCP established, keystrokes to users, la-da-da-da-da-da, but it is not secure. It's one of the keys to this one. It's a basic command line connection. We might as well, since I've already got everybody miserable. No, let's What would we see if we saw a Telnet session, for instance? If I could spell 54, I think, username. So when I get there, nothing really fun. It says switch. I'm now telnetted to the switch. I'm actually connected to that switch in the back of the room. So I could do configurations on it. We can look at the things that are up and the down and those sorts of things. So I can use this in order to check my port security out. Nobody's tried to do bad stuff. Because see, when I gave this security violation count, I don't have any security violations on the ports. But what I have done with the Telnet session is connect to some remote device. You can Telnet from a Windows machine to a Windows machine, but by default it's turned off. You have to go turn the service on in order to do it. You can have a client or a server. So I think what it is used a lot for, and actually now instead of using Telnet, you're probably going to use a secure protocol called SSH, Secure Shell. But I can Telnet connect to a basic session at a remote device and manage it using Telnet. Problem is it's insecure. Somebody were able to see my traffic, they'd see everything I was typing. FTP, go back, FTP, File Transfer Protocol, another application layer protocol, another actually non-secure protocol. If you use, there's a secure FTP also. FTP not only can see all the stuff you put in, like passwords and things like that, you can actually read the data. You can actually read the text if you're transferring a document. You can actually read the document in FTP. Anonymous logons are available, and when we talked about earlier today, a lot of the scans on us is for FTP. They're looking for anonymous logons. Anonymous means you have to have a username and password. You do have to username and password. The username is anonymous, and the password is some made-up email address, whatever. It's just got to be in that format. My favorite one to use for my anonymous logons are bill@microsoft.com. TFTP, Trivial File Transfer Protocol, the file transfer between components is simpler than FTP. It's a UDP protocol. FTP runs on TCP, TFTP, Trivial File Transfer Protocol, runs on UDP.
Big protocol, is that what you're saying?
I'm sorry?
Just like a protocol, and then inside the protocol, there can exist another protocol?
Well, because we have to have, when we connect it, we either have to use TCP or UDP at layer 4, right?
Okay, yeah.
So if we're going to connect to, if we're going to use the FTP service, we have to use the TCP layer 4 protocol.
Okay.
If we use the Trivial File Transfer Protocol, which really is a much simpler one, we use UDP.
Okay.
This one, the TFTP, big use for it is to transfer configuration files from routers and switches to store on your computer so that if they crash. The beauty of the beauty of Cisco is that if something happens to your machine, you put a new one in. If you upload your configuration file, you're back in business. You don't have to go back and put everything in again. As long as you save that configuration file and you transfer it from one device to the other using the TFTP protocol. We'll do that in the routing session. NTP, Network Time Protocol, port 123. It's also a UDP protocol. It synchronizes the clocks. There are a number of, and Sharon was on Ranger the other day. Has got a lot of utilities on there. I think there are a couple of time. If you go to / Ranger, there's a folder that's got utilities, and some of them are really, really old because it's one of those things that I put on. I never take anything off. But it's got some time servers in there if you want to do that. Microsoft machine should synchronize time. They sometimes do well, sometimes don't do well. Time is not a matter of everything having the correct time. They all need the same time. So that if you need to do troubleshooting, you know what happened when relatively speaking on your machines. NNTP, Network News Protocol, I don't see that one come up a lot anymore. It used to in boards. Ping, Packet Internet Groper, that's what they say. So ping is the utility we use to do an awful lot of troubleshooting. Is it alive? And also traceroute. Traceroute checks the route, basically does. Not basically. Ping checks to see if there is what's called a live machine at the other end. It's an Icmp protocol in Windows. There are other utilities. One called hping uses TCP, so if you don't get an answer with one, you get another one. It's echo request and echo reply. Ping and loopback address 127.0.0.1 is the first thing you should check if you have connectivity problems with your computer. Ping the loopback 127.0.0.1, then ping the actual IP address, and then start working your way out into troubleshooting. It does have some switches. It says many useful switches. I think the most useful switch is the -T, because ping by default gives you 4 shots, right? If you use -T, it keeps going until you do Control-C to stop it. You can also tell it how big you want the packet to be if you want to try some of those other clever things with it. IPX, SPX, kind of gone, dead. If you see that, NetWare. Netbios and NetBEUI, originally designed to provide transport and session layer for applications running on small, homogeneous networks, broadcast networks. They're all right there together. Microsoft added a standard transport layer called the NetBEUI. NetBEUI is Microsoft's version of the NetBIOS protocol. Let's assign a NetBIOS name. Look at this call. The addressing is, you assign a name. The name is the computer name. The computer name, 16 characters. The 16th character is used for what they call membership, so it's actually 15. If you ever try to make one of these things a real long name on a computer, you can't do it. You're limited to 15 actual characters. Workstations, it discovers the MAC address, same, uses the address for further communication. NetBIOS broadcast protocol is not routable, and that's, I think the key to that, it's not routable. It's still there. Does Windows need it anymore? No. Do other services need it? Maybe. This is, well, how, if you're using this, how do you find another computer if it's a broadcast protocol? Of course, we always add something. We add another service called WINS, Windows Internet Naming Service, which is also called an NBNS, NetBIOS Name Server. What it does is list the NetBIOS names and the IP addresses so that you can look them up and get them. Used exclusively with Windows systems using NetBIOS, and it is a Windows thing. NetBIOS is a Windows thing. Linux machines don't use NetBIOS; they use IP. Strictly use IP addressing. AppleTalk, 8 or 16-bit number, said the only thing, honestly, the only thing I've ever seen in AppleTalk. Yes, it's still there. Yes, it's still very slow. Yes, it's not used. Apple uses the same thing everybody else uses, TCP IP. An 8 or a 16-bit number, that's not very big, is it? It's either 1 or 2 bits, 1 or 2 numbers. With 10.60.211. something was a 32-bit number. So an 8-bit number would be like 1. A 16-bit number would be like 10.60. So that's binding protocols, processes of assigning a component from one to the other. I think they got some activities, and I'll make you some virtual machines to do these. Attempt to bind the network interfaces on the computer. Bind just means it's associated with. It's a term they use. We would bind a protocol to it. We associate that protocol with the service. Bind only those absolutely needed. And an example of that, again, back years ago, somebody was using a Windows 2003 server, and he just decided to put all the protocols on it. Well, he messed up, and he put the wrong DNS server in. So Active Directory didn't work out so well. It took about 40 minutes to get logged on because he had to wait for each of the protocols to time out before he would quit trying. Only enable the ones that you need. Not such a big deal anymore. They used to put, they used to put a list of about 4 protocols. Now it's a list of about 2, IPv4 and IPv6. That's okay, but only put the protocols on that you need, and it's not a big deal. You can just uncheck them or uninstall the protocols, whichever you want. You may need multiple protocols. If we were in a situation, which we're not, that we had NetWare and Microsoft running, we might need TCP and IPX. So you could have both of the protocols bound to the same NIC. And I told you it wasn't long. You thought I would never get here, didn't you? So what do we ask to see if we have to start over? How about IP addresses? Tell me about them.
Well, there are several IP addresses. There's only one MAC address.
Only one MAC address, and that's good. And Yep. So IP addresses are variable or dynamic. We use the DHCP, Dynamic Host Configuration Protocol, service on a server to automatically assign them so that we don't make typing errors. So we all get on the right network. And we use the ARP protocol to relate the IP address to the MAC address so that we can find the computer. Exactly right. The services, we looked at the header a little bit. We'll do some more header, and I think there's a couple of things in the activities to look at some header information. That's some Wireshark information. It's kind of interesting to do when we look at these things. What I did want to do, let me click through here quickly, hopefully quickly, is to look at a little bit of this stuff. This morning, I turned on Wireshark in the office for, I don't know, maybe 15 or 20 seconds and got this much data. We talked about the startup. Here we have the SYN packet, the SYN, the SYNAC, and the ACK. And you notice I'm going from 1060, 61, 175, the machine in the back, to 98. I was going to, in this one, I was going to yahoo.com. I have a DNS lookup. We'll go back and look at that just in a second. HTTP SYN, the sequence number, when the Windows size, 8192. The length, maximum segment size, 1460 byte workstation. SAC is Selective Acknowledgement. When we go down here to the SYNAC, we got the 386 here, and we go to 387 over here. So we have the 1-bit incrementation in the sequence number. I start a new one. Because the other system said, okay, I'm going to have my own number system. And then
you say something about the
phantom byte, but because in these there is no data in the three-way handshake. There is no data being transferred.
Okay.
But since the sequence in the acknowledgments based on the amount of data in the three-way handshake, you automatically increment it by 1, as if they were, because there's no data. It's called a phantom byte because there's not really 1 byte of data.
Okay.
We just pretend that there is. So it's the pretend byte, the phantom byte. It's called a phantom byte because we have to increment it so that we don't have these being the same number. And then we have a sequence number here, 275. It goes to 276. The sequence number here stays the same. So the three-way handshake goes here. A couple of other things that I think showed up on here. There's some other SYNs. We had a DNS query. Let's see if we see if there's anything interesting in this DNS query. DNS queries, yahoo.com, and then I got the answers. 98, 139, 183.24 eventually. So we've looked for an address, and we eventually got that address. Let's see if we can. Yeah. It's not going to let me do what I want to do, so. Thought there was some DHCP stuff here. See, TCP, HTTP, MBNS, Netbios name server, there is one out there. ARP. We talked about ARP. What ARP does, here it says ARP. Who has 10.60.61.254 till 10.60.61.225? So this machine's looking for the MAC address for this IP address. That's what an ARP request would look like. Spanning tree. There's a DHCP. Here's a DHCP we get to discover in the offer in here, the Bootstrap protocol. But message request, and notice that we're getting 0. 0 means any server. Anything that's all zeros means any. As we go through these things. TCP, ARP, nothing other dramatic on there, is there? How many of you use Dropbox? It has this little funny thing, unless you configure it not to, it broadcasts. And that's what that is right there. Dropbox, LAN Sync Discovery Protocol. Everybody that's got Dropbox around here is advertising themselves. Go up front and look at that little display and watch this. There's a Wireshark there. Look and see how many of those are Dropbox.
You mean like the school's Dropbox?
No, it's not the schools. The individual people that put Dropbox on their machines.
Yeah.
You can configure it to not do that, but most people haven't. Questions? Ready for me to quit, aren't you?